Hello everyone! I'd like to welcome you today to my poster presentation. My name is Bengisu Sisik and I'm a PhD student at the George Washington University. Today, I'm going to present you our research, the influence of leg shape on thermoelectric performance under constant temperature and heat flux boundary conditions. Thermoelectric devices offer the potential to convert wasted heat into electricity. As you can see on figure 1, NNP-type thermoelectric legs are the main constituents of the device. When a temperature gradient is formed between the ends of thermoelectric legs, electric current flows in the circuit. The goal of this work is to investigate the impact of leg geometry on the temperature and electrical potential gradients across the leg. In that purpose, 9 different leg shapes were selected for this study. The baseline is a rectangular prism, as this shape is the standard leg geometry found in commercial thermoelectric modules. The other shapes studied are trapezoid, reverse trapezoid, hourglass, inverse hourglass, Y-shape, reverse Y-shape, hollow rectangular, and multi-hollow rectangular shape. The choice to confine all shapes to the same volume stipulates that the fill factor is the same regardless of the leg shape, and thus the findings are extensible to other leg lengths. The boundary condition combinations applied to 9 leg shapes resulted in 270 simulations. The specific hot side boundary conditions were selected based on the temperature range in which each thermoelectric material's figure of merit is the highest. The numerical modeling is conducted with COMSOL multiphysics software. We input the boundary conditions presented above and obtain the electrical potential gradient as well as the short circuit current from the simulation results. With these parameters, we then find out the electrical resistance and the maximum power output is calculated by this equation. The results presented in this poster reveal the conditions under which variations in the thermoelectric leg shape have the most impact. For constant temperature hot side boundary condition, in terms of power generation potential, the most advantageous leg shapes are the trapezoid with 93%, hourglass with 104%, rectangular hollow with 78% higher power output than the conventional rectangular shape. The transfer silicon germanium are the same. These shapes have larger thermal resistances, therefore they perform better. Figure 5 shows how the power generation potential varies as a function of load resistance for various leg shapes with a low cold side forced convection. The rectangular prism is represented by the blue star, and we see that greater power generation potential is obtained with the hourglass, trapezoid, hollow, and multi-hollow rectangular shapes. Since constant temperature boundary conditions are much harder to realize in practical applications, it is useful to consider a hot side constant heat flux boundary condition. The cross-sectional area of the leg at the hot side is pertinent under this condition because the heat transfer rate into the leg is the product of heat flux and this area. Therefore, leg shapes with a larger cross-sectional area at the hot side result in more heat input to the leg, and the most advantageous leg shapes are thus reverse trapezoid, hourglass, and rectangular hollow shape. Here, we see the change in performance for the hourglass shape for various cold side boundary conditions. Under the hot side constant temperature boundary condition, the advantage of changing leg shape diminishes as the cold side convection coefficient increases. In the case of constant heat flux boundary condition, the advantage of the leg shape persists for all the cold side boundary conditions. As a conclusion, we understood that the rectangular, so the conventional leg shape, is not the optimal shape for heat-to-power energy conversion. For example, the hourglass shape, subjected to constant temperature hot side boundary condition, has the best electrical and thermal performance. As new methods for manufacturing thermoelectric legs advance, novel geometries become increasingly accessible. Thus, understanding the coupling of the boundary conditions with the leg shape becomes critical to the thermoelectric device performance. Thank you very much for listening to my poster presentation.